Hello and welcome back to section 9.1. In this video we'll be using example 1 to demonstrate how to find the centroid of an area. So the book's going to walk you through some of these methods that I've outlined in procedure, and one of their methods looks at using a differential area. So for instance, we have this one here where we have some differential x side and then a full y. So I know I can't draw. I'm using a mouse to draw with this, so it's not quite squared. But so that's the area there. There's another one over here. That one a little bit better. And that works. The difference is you have to be able to know when to use parallel axis theorem and when to not use parallel axis theorem. So for example 1, you could use this method, and if you read through the book and you understand it and you like it, go for it. But what I'm going to do is I'm going to do a double integral to solve this, because that's a different method you can use. Alright, so I've redrawn our problem here. We have this area underneath the curve. We have y equals x to the third, which describes our line here in yellow. And so what we're going to do is decide how we're going to differentiate this. So I'm going to make some differential area, and I will make it red. So we have this differential area. It has some height, delta y or dy, and some width, dx. Now if you're using the rectangles that they show you in the book, you'd have one of these be, say, dy, and you'd have an x, or you would have a dx and a y. And you could solve it either way and it would be fine. But I'm going to use double integration. We're trying to find x bar and y bar. So we know from the set of notes that x bar can be written as the integral of x tilde d area over integral d area. Now our d area, so let's go back over here. The area of this infinitesimally small piece of whatever this, a square thing here, we can write this as dy dx. We can also write it as dx dy. And the order does matter. So we want to choose the one that lets us start at 0, if we can. So if we look at our problem, I have essentially, if we do a double integral, we're going to integrate from one line to another line for the first integral, and then for the second integral, we're going to go from a point to a point on the kind of the last line. So if we integrate and say the y direction, we would start from this line here, which is a line that's described by y equal to 0, and then we would go up to this line, which is the line described by y equals x to the third. The other option, and so that would be integrating in the y direction first. If I went in the x direction and I went left to right, I would go from this line, which I would write as x equal to y to the 1/3, so we'd have to rearrange that. And then I would go over here to this line, which is described by x equal to 1. And sorry, I'm using a mouse to do all this drawing. I don't have a tablet. So of given those options, I would much rather go from a 0 than from a variable to a non-variable to a constant. So I'm going to go with dy dx first, because we get to start at y equals 0, which is nice. Again, that's the initial line. So we will integrate, double integrate, and then we're going to go dy dx, and we're going to integrate from 0 to, from 0, because it's y equals 0, to y equals x to the third. So we're going from two lines here. We'll have the same bounds down here, dy dx, and then the second boundary here is for the dx, and so when I get to the end, my x will span from 0 to 1. So just 0 to 1 out here, because those are just points. And then hopefully you remember how to do your integrals. So we'll integrate this so that we're going to be left with a 0 to 1. We're going to get x, and now we're integrating with respect to y. So y is going to pop out of this. We're going to evaluate this from x to the third to 0. Down here, 0 to 1. We have a constant 1 in here, so if you need to, just write that 1 so that you remember it's there. You're going to get a y that pops out here. We're going to evaluate that from x to the third to 0. So we get this. So what we get here is we get x times x to the third. That's why that 0 is nice, because otherwise you have to do the subtraction, and it makes it kind of messy to deal with. So we get x times x to the third, which is x to the fourth dx. This just becomes an x to the third dx. We integrate that. So now we're integrating with respect to x. And the things that happen as you think they do. We get x to the fifth over 5 from 1 to 0 divided by x to the fourth over 4 from 1 to 0. And that becomes 1/5 divided by 1/4 for a total of 4/5 or 0.8 meters. And so that'll be you can't see any of that, sorry about that. So that'll be 0.8 meters starting from here in the x direction. So it'll be 0.8, so it'll be over here. And think about it logically. It would make sense that it's over here in the heavy, kind of the fatter area of this almost rectangular shape. If we approximated this as a rectangle, we'd expect it to be 2/3 from this side or 1/3 from this side. So it seems about right. All right. So repeat the same process for y bar. Y bar, double integral. For the same reasons, I am going to do dy dx because I want to start with that 0. You can go with dx dy. It's completely fine. So now we're going to go y tilde dy dx. We're going to go from 0, x to the third, 0 to 1. So the thing about the bottom, I have no reason to actually do this math. We already know what this equals. It is equal to a quarter. So we'll just put the quarter down there and save ourselves the steps. So I'm just going to move it over here for right now, okay? So I'm just going to have 4y bar equal to the integral from 0 to 1. We're just going to integrate the top right now, and then we'll put this 4 back over when we need to. All right, and if it helps, you should probably just call this y instead of y tilde, because at this point it is just y. It's just the distance. So it's the distance in the y direction to this box as we move the box around. So it's just y. All right. So y dy becomes y squared over 2. Integrate that from x to the third to 0, and then dx. And again, down here we're not going to do anything. So 4y bar. So what we're going to get, so again the 0 means that I won't get anything, so I won't do any subtraction. So it's just going to be x to the third squared over 2 dx, and we can simplify that. And that'll become x to the 6 over 2 dx, and now we're integrating an x with an x. So we get x to the 7th, 7 times 2, from 1 to 0. So we will get a 1 on top, a 14 on the bottom. And then, remember this is 4y bar, so that means y bar is a... sorry, that's not a 4y bar. That should be a quarter y bar. There's a quarter on the bottom, so this should be a quarter all the way down. That makes more sense. We should get 4 over 14, or 2/7, which is a fraction of 0.2857 meters, and that's going to be up from the bottom. This will be to the right. All right, and so we could say the centroid is at 0.8, 0.286. So that's where the centroid is. And again, as we go back up here, that makes some sense. 0.8 puts us over here, 0.2 puts us down here. So logically, it also makes sense. All right, if you have any questions, feel free to reach out.